In this lecture, we use a frequency response approach to design LagLead compensators. A lot of what we'll do here builds off what we've already learned about designing lag compensators and lead compensators using the Bode diagram. The basic structure of this lecture is as follows. First, we'll review what we know about lead and lag compensators and compare them. So this will be a little bit of a review, and it'll help to motivate why we might want to combine the two types of compensators to create a lag-lead compensator. We'll then give a brief overview of the procedure we'll use for designing a lag-lead compensator with the Bode diagram, and then finally we'll go through a relatively detailed example. So if we recall, lag and lead compensators have the same basic form. They have a gain and a single zero and a single pole. The only thing that's different is the relative size of the pole and the zero. In the case of a lead compensator, the zero is smaller than the pole. And so in that sense, we think of the zero as being slower and as dominating the response. It's opposite for a lag compensator. In a lag compensator, the pole is smaller, and so that dominates the response. In many instances, a lead and a lag compensator can both meet the requirements that we have, especially in many cases that's true. And for example, we've been trying to design our compensators basically to meet steady state error requirements and overshoot requirements, and we've been able to achieve that with lag compensators and lead compensators. And so the question you may have is, which approach is better? And basically it depends on what your goals are. And so we'll try to clarify that a little bit. So here is an example of a lead compensator. We have a gain, we have a zero, where the zero is smaller than the pole. This is the shape that we generally expect from a lead compensator of its Bode diagram. And so in this case, we have some DC gain, greater than 1. And then at higher frequencies, the magnitude increases even more. And the lead compensator adds phase lead. And so the purpose of that, or how we design it, is so the DC gain from the compensator helps to increase the DC gain of our open loop system. So the blue line is the plant by itself, and then the red dashed line is the plant with the lead compensator. And you can see the effect of adding the lead compensator was to increase the DC gain. And we commonly do that to help improve the steady state error. We also see that we increase the magnitude of the open loop system even more at higher frequencies. And that tends to have the effect of pushing the gain crossover frequency out, which tends to speed up the system's response. And it can also have the effect of not attenuating high frequency noise as much. And then when we designed the lead compensator, we designed it to try to add this phase lead in the area of our new gain crossover frequency. And so in general, we try to add this phase lead in order to improve the overshoot, because that is what correlates to phase margin. So in this case, we're achieving a phase margin of approximately 45 degrees. And so, that was sort of the effect. One thing that we will sort of notice when we design a lead compensator is that we can't really independently choose the gain crossover frequency and the phase margin that we're going to achieve, or the phase margin that we're going to add. And the reason that is because the magnitude plot and the phase plot of the Bode diagram for the lead compensator, they're connected. You can't design the magnitude independent of the phase. Anytime you add a zero, anytime you add a pole, you affect both, and they're sort of tied together. And so the issue that we can have when we are trying to use lead compensators is we may not be able to achieve the gain crossover frequency we desire independent of the phase margin we desire. We have a limited amount of freedom in our design. In the examples we've done so far, we've sort of focused on meeting the overshoot that we wanted, and we didn't really try to achieve a certain level of speed or a certain gain crossover frequency. Looking at a lag compensator, so here you can see a similar form, a gain, a zero, and a pole, but in this case the pole is smaller. And so if we look at the Bode diagram, here we have increased the DC gain, but whereas with the lead compensator the magnitude increased at higher frequencies, here the magnitude decreases at higher frequencies. And instead of adding positive phase, here we add phase lag, negative phase. And the way that we design it, so we add it to our plant, and we can see that by increasing the DC gain, again, we help the steady state error. Comparing to the lead compensator on the previous slide, we increase the DC gain a similar amount. We then choose how much reduction in gain. So this is sort of the ratio of pole and zero determines the reduction in gain, in order to move the gain crossover frequency to a location where our plant has the amount of phase margin we desire. Okay, so whereas with the lead compensator, we use the phase lead from the compensator to help our phase margin. With the lag compensator, what we do is we shift the crossover frequency to a point where the plant naturally has more phase margin. Okay, so it's a little bit of a different strategy. Here, the phase margin is a little bit more than 45 degrees, but let's say it's similar to almost 45 degrees, which was what we achieved with the lead compensator. When we center this bump in phase lag, basically our approach is to put the bump 1 decade before our new gain crossover frequency, because this phase lag is sort of detrimental in general. So we try to keep it away from the crossover frequency, and we shoot for about a factor of 10 below the new crossover frequency. Here you can see, based on the red dashed line, that the compensator does add a little bit of phase lag to the plant. We could reduce that by shifting this bump even earlier, placing it 2 decades below the crossover frequency. The reason that we try not to do that is because shifting this bump earlier makes us add a slower pole. And so if we make this pole too slow, it can have detrimental effects on our time response. And oftentimes we can see that with this sort of very slow tail on the step response. So that's the basic approach for the lag compensator. You can see that again we sort of have a limited amount of freedom in our design. We sort of chose the crossover frequency to achieve a certain phase margin, but we can't really design them independently because the magnitude and the phase are connected together. So let's go ahead and compare the lead and lag compensator we just showed. So in looking at those two examples, they both achieved relatively similar DC gains. And so in this case, the steady state error to a step will be a 0 in both cases because the system was type 1, the plant had an integrator in it. If we looked at the response to a ramp, they would both also have the same steady state error. They also had similar phase margins, and so because of that they achieve similar overshoots. The lag compensator had a little bit more phase margin, but similar overshoots. The thing that is different between the two designs was the gain crossover frequency. And so the effect of that, since the lead compensator gave us a higher crossover frequency, it is much faster. So it reaches its peak much sooner, and the lag compensator reaches its peak later. So the big difference, we achieve similar steady state error, similar overshoot, but the lag compensator is slower. And so in general we would say, well, faster is better. We want a fast response, we want to drive the error to 0 as quickly as we can. The drawback, though, of that speed is the amount of control effort it requires. So if we look at this second plot, where again the lead compensator is the blue line, the lag compensator is the red line, we can see that the lead compensator requires much more control effort. So it has larger peaks of control effort, so that indicates needing a larger actuator. And overall, the control effort is larger. For example, if we integrated this control effort over time. And so that could correspond to needing more fuel or needing more power from a battery or whatever. So in essence, that's the basic trade-off between these two compensators, and which is better really depends on our definition. Is it more important to be fast, or is it more important to be cost effective? That's the basic trade-off between these two compensators. The other thing that we sort of saw was we had a limited sort of freedom in the design of our system. We could sort of achieve the speed that we desired, the gain crossover frequency we desired, or the phase margin we desired, but it was difficult to accomplish both because the phase and magnitude were tied together. And so something that we can do is we can combine a lead and a lag compensator to give us more freedom in our design. Okay, so this is the basic form of the LagLead compensator that we're going to design. It basically gives us more design parameters to use. The first part we'll call our lag compensator. It'll consist of a gain, a single zero, and a single pole, where the ratio of that zero to pole is greater than 1. So the pole is slower for our lag compensator. We will then add to that a lead compensator, where this lead compensator has a DC gain of 1. So we'll do all of our DC gain change with the lag compensator. Same similar form, 1 0 1 pole. The only difference is that the 0 is smaller in this case. So this is the basic form of the compensator we're going to design now. The approach that we're going to use is as follows. First, we're going to try to design a lead compensator all by itself and see, there's sort of two reasons for this. One, we'll see, can we meet our requirements with only a lead compensator? We'll design it initially to achieve the steady state error we desire and the overshoot we desire. That is the approach that we took in the previous lecture. So you can refer to the previous lecture on how to do that. The other reason that we're going to do that is it's gonna give us sort of a benchmark from which to calibrate our design. In general, steady state error we can meet pretty easily because we use the final value theorem, and the final value theorem really holds no matter what kind of system we have, what order it has, whether it has zeros, whatever. We then try to achieve our overshoot on the basis of our phase margin. That relationship between overshoot and phase margin, or phase margin and the damping ratio, is a little loose, especially when we don't have a canonical system, but it gives us a place from which to start. But it's not an exact relationship. Similarly, we don't have an exact relationship between speed and crossover frequency. We only have kind of a qualitative relationship. We know if we make the gain crossover frequency larger, we'll be faster, but we don't know how much faster. Same thing with overshoot. We know if we increase the phase margin, we'll reduce overshoot, but we don't know by how much. And so one reason for doing this lead compensator in the first place is it gives us a benchmark from which to tune our system. We can say, okay, for this phase margin and this gain crossover frequency, this is how fast we are, this is how much overshoot we get, and we can try to tune based on that benchmark. In the second step, we look and see how well does the lead compensator work. Is it close to meeting our requirements? where in this case we're really trying to achieve three things simultaneously. Previously we sort of were only trying to achieve two things, but now we're going to try to achieve three things because we have this extra degree of freedom. So we'll look at the DC gain, but we'll also try to achieve a certain amount of overshoot and a certain speed of response. And so if the lead compensator all by itself is close to meeting all three requirements, or if it's too slow, we can try to tune the lead to speed up and meet the overshoot if we can. If the response is too fast or faster than necessary, or we're really having a hard time meeting all three requirements with just a lead compensator, we're going to move to step 3 and start over. So we'll throw out the lead compensator we've designed. And in essence, we're going to do our LagLead. When we do our LagLead, we're going to start with the lag compensator. We're going to design it to achieve 2 out of our 3 requirements. We're going to design it to achieve a certain steady state error, based on the DC gain. And we're going to try to achieve a certain gain crossover frequency, and we're going to calibrate it based on our experience from step 1. So we'll try to meet sort of 2 out of the 3 with the lag, and then in step 4 we'll add a lead to that in order to achieve the last requirement, which was the overshoot. The final step is to check the results and iterate. This sort of compensator is more complicated. It has more design parameters that we can tune. And so in this case, the iteration process can be more involved. And we may even wish to sort of iterate at step 3 in order to achieve omega c, and then iterate again in step 4. But that's the basic approach that we will take. I'm going to try to illustrate that approach with this example. So here we're going to use a system that we used previously. Specifically, we used this system when we were designing a lead compensator in a previous lecture. So it's a standard unity feedback system. Our plant is an underdamped second order system, and we're going to design a LagLead compensator to meet these 3 requirements: a certain level of steady state error, a certain amount of overshoot, and a certain peak time. So we did this example previously where we designed a lead compensator, but we were only trying to achieve 2 out of the 3 requirements. Now we're going to try to achieve 3 requirements, and we're going to use the extra freedom that the LagLead compensator provides us. So the first step is to design a lead compensator all by itself. This is the basic form of a lead compensator. We're going to follow the same procedure that we did in the previous lecture, where we're trying to achieve a certain steady state error and a certain overshoot. In that previous class, when we followed our procedure, this was the design that we arrived at. Now, this gain achieved our steady state error. This pole and 0 it helped us to achieve the overshoot that we desired. Based on this lead compensator, we then go ahead and look at the time response and see how it fares. And so if we look at this, the steady state error is exactly 0.05, which we designed for. The overshoot is a little bit larger than 5%, so we would maybe want to go back and increase our phase margin. But the big difference is the speed. So it meets the requirement. We desired a peak time to be less than 1.5 seconds, which this easily does. But it's quite a bit faster than necessary. So we could be happy with this speed of response, but the drawback is it's likely requiring us to use a larger actuator and more energy or power than we might otherwise need to. So what we're going to do is we're going to sort of throw out this lead compensator. and tried to design a LagLead compensator in order to slow the system response down a little bit while still meeting the requirement and also bringing the overshoot down. In order to sort of figure that out, how much do we need to change the crossover frequency, we go ahead and look at the Bode plot. So the peak time that we achieved was 0.179 seconds. Our requirement was only 1.5 seconds, so we're basically 8.5 times faster than necessary. We're going to use this proportion in peak time as a measure of how much to change the crossover frequency, because crossover frequency corresponds to speed of response. So if we look at the Bode plot, this blue line was the plant all by itself. The red line is our lead compensator with our plant. And so for this lead compensator, we achieved an open loop crossover frequency of 17.3 radians per second. We're going to use this as an indication of corresponding to a peak time of 0.179. And so what we're going to do is we're going to decrease the crossover frequency in a similar proportion to the amount that we want to decrease the peak time. If we were going to be exact, we would take that 17.3 radians per second and divide it by 8.5, because that was the ratio between the peak times. Here we're going to be a little bit conservative and not slow it down quite so much to make sure that we're still well within the 1.5 seconds. And instead of decreasing it by a factor of 8.5, we're going to decrease it by only a factor of 5. So we're going to shoot for a crossover frequency of 3.5 radians per second. Okay, so this sort of illustrates one of the purposes of doing the lead compensator. One, we try it to see if we can meet our requirements with only a lead, but the other reason we do it is to give us a benchmark from which we can determine how much to play with the crossover frequency. So since we're going to do our lag lead, we throw out the lead that we designed and we start over and design a lag compensator. Here we're going to only try to achieve 2 of the 3 requirements, the steady state error and the crossover frequency. The procedure that will follow will be similar to what we did previously in a previous lecture, but in that lecture we weren't trying to achieve a particular crossover frequency, we were trying to achieve a particular overshoot or phase margin. This is the basic form of the lag compensator we're going to design. In order to achieve the steady state error, we know that this is the amount of DC gain that we need contributed by the compensator. This we found previously, it still holds. So we still, if we do the final value theorem and solve for K, this is still the amount of DC gain that we needed contributed by the compensator. We're then going to choose our ratio of zero and pole, which is our beta, in order to reduce the magnitude at higher frequencies to achieve this amount of gain crossover frequency. So this is the Bode plot of the plant with our K equal to 95. So adding this K bumped up our DC gain just as we desired. With a lag compensator, we need to figure out how much gain reduction. So we're going to bump up the magnitude at low frequencies, but then we're going to drop the magnitude at higher frequencies. And this amount of drop is going to be determined based on where we want to place the crossover frequency. So we want to place the crossover frequency at 3.5 radians per second. If we look at the magnitude at that frequency, the K times P has a magnitude of 15.6 dBs. So that is the amount of gain reduction that we need in order to achieve our new crossover frequency at 3.5 radians per second. Okay. Recalling, decibels is arrived at by taking our gain and taking the logarithm of it and multiplying it by 20. So if we want to solve for our beta, we simply take our 15.6 dBs, divide by 20, and then raise both sides to the power 10, because this is a logarithm that's base 10. So if we do that, we arrive at a beta of 6.3. So that ratio of pole and zero determines the gain reduction that will allow us to achieve the desired crossover frequency. Very similar to what we did before, but before we were trying to achieve the crossover frequency to correspond to a certain phase. We then need to determine where to center the pole and the zero. So we've got our beta, which is the ratio of pole and zero, but then we need to figure out where to center the pole and zero. In general, we're going to center it, such that the maximum phase lag is a decade before our new crossover frequency. So our crossover frequency that we're trying to achieve is 3.5 radians per second. A decade below that, a factor of 10 below that, is 0.35 radians per second. So that's where we're going to try to place the center of the zero and pole, so that the phase lag is sort of away from our new crossover frequency. We could try a larger factor than 10. The problem with that is that it tends to add a slow pole, which is detrimental. It makes the system response slower. So once we have these two relationships, the ratio of the pole and the zero, as well as where to center the pole and the zero, if we recall, this center is at the geometric mean of the pole and zero location. So between these two relationships, we have two equations and two unknowns, our zero and our pole. We have enough information to sort of solve for Z and P. We can sort of solve one equation for P and plug it into the other equation and solve. I'll skip that step, but if we do that, we arrive at a zero at 0.88 and a pole at 0.14. Okay, so that sort of determines this part of our compensator. The last thing to do is to calculate our Kc. So overall, from our entire compensator, we need a DC gain of 95. That's what we determined previously. Some of that DC gain is going to come from this beta, this ratio of the zero and the pole. And the rest of it's going to come from this Kc. So in total, we need 95. Some of it comes from Kc, some of it comes from the pole zero ratio. And so in order to solve for Kc, we simply take the 95, divide through by the beta, which is 6.3, and we arrived at a Kc of 15.1. So that is our lag compensator. So this is the plant. This is the lag compensator that we designed. If we look at the Bode diagram, this is what we get. And if we look at the step response, this is what we'll also see. We'll see that our steady state error is met, and we'll see that the speed is slowed down. So we took an original crossover frequency of 17.3 and we reduced it to almost 3.5. So if we looked at the step response, we could see that we've slowed the response down and we're meeting the steady state error. We will likely not be meeting the overshoot yet because we didn't design for it. A smart thing to do at this point would be to go ahead and iterate on the design of our lag compensator. So look at the step response, look at the peak time, see if we can slow it down even more, see do we need to speed it up. So that would be a smart thing to do. In the interest of time, I'm going to skip that and move on to adding the lead compensator. Okay, so we'll say we've got our steady state error, we've slowed it down, which is what we were trying to achieve, and then we're going to add a lead compensator in order to add some phase margin so that we achieve the percent overshoot we desire. So here we sort of follow a similar procedure that we did when we designed lead compensators previously. We desire an overshoot less than 5%. That is achieved with a damping ratio of greater than 0.7. We have this approximate relationship that zeta is approximately related to phase margin by this relationship. This doesn't hold very well for zetas greater than 0.6, and it also doesn't hold very well if we don't have a canonical second order system, but we'll still go ahead and use it as a starting point. So if we use this equation, a damping ratio of 0.7 corresponds to a phase margin of 70 degrees. So this is what we're going to try to achieve. If we look at the previous slide, our phase margin is approximately 51 degrees. And so if we want to achieve 70 degrees, we're going to need to add some phase margin. We're going to need to add some phase lead with our lead compensator. So it's about 51.4, 51.2. That corresponds to about 18.5 degrees of extra phase that we need to add. If you recall, when we add the lead compensator, it's going to push the crossover frequency out some to a location where we have less phase, where we're going to have less phase. So to account for that shift in crossover frequency, we're going to add a little bit extra to this 18.6. And so let's say we're going to shoot to add about 25 degrees of lead to our phase margin that we've already achieved. This amount of phase lead is going to determine the ratio of the zero and pole that we're going to use in our lead compensator. We call that alpha. And so if you recall back, we have this equation for alpha based on the amount of phase that we want to add. And so here, if we calculate this, we need a pole-zero ratio of about 0.406, or a zero-pole ratio. When we do this, when we add this, we're not only going to get a bump in phase lead, but we're also going to increase the magnitude at higher frequencies. And in particular, we're going to try to center this bump in phase to be located at a new crossover frequency. And so it turns out that at this center of the bump, this maximum phase lead that we're going to add, the magnitude added by the lead compensator can be calculated with this equation. And so at the phase bump, we're going to add 1.57, a factor of 1.57 magnitude. If we convert that to decibels, we're going to add about 3.9 dBs at that center. So here again is our KP, this blue line. So if we look at the KP, so this is, my apologies, this is the Bode of the whole thing with our lag so far. So the lag compensator with the plant, the lead compensator is going to add about 3.9 dBs at the center. And so if we look at this Bode plot, we're approximately 3.9 at approximately 4.6 radians. So we're at negative 3.9 dBs at 4.6 radians per second. When we add the lead compensator, we're going to add some magnitude here. That's going to move the crossover frequency to that location. And so what we want to do is we want to center our bump in phase lead so that it's located at this new crossover frequency so that we're getting the maximum benefit to our phase margin. Okay, so that's what I was sort of saying. We calculated the alpha to give us the amount of phase bump, and then we centered the pole in the zero so that the phase bump is located at the new crossover frequency. So between those two relationships, we can then solve for the pole and the zero of the lag compensator. So the ratio of zero to pole is 0.406. The geometric mean of the pole and the zero, where we center the bump, is 4.6. We have two equations, two unknowns. We solve for those, we get our zero is approximately 2.93 and our pole is approximately 7.22. So that completely determines the lead compensator that we're going to add to the system. Again, we have no additional gain. This part has a DC gain of 1. The reason that is because we're achieving all of the change in DC gain with the lag part of our compensator. So altogether, this is our compensator. So this is the lag to achieve the steady state error and the crossover frequency we desire, approximately. And this is the lead to then add some phase lead to give us the phase margin and overshoot that we desire. The last step then is to check the closed loop step response and see how well does it perform. So here's our response. We are achieving our overshoot. It's less than 5%. We're achieving our steady state error. It's exactly 0.05. And we're achieving our peak time, which is less than 1.5 seconds. So all of our requirements are met, and we've slowed the response down as compared to what we achieved with the lead compensator all by itself. We're still quite a bit faster than necessary. We're still well below 1.5 seconds. So if we wanted to, we could iterate on this design and try to slow it down even more. I won't do that, just in the interest of time. One other thing that I'd like to point out, here you see that we have this sort of slow tail on our response, and that's sort of due to the slow pole of the lag compensator. So this sort of motivates why we don't put the center of the 0 pole more than a decade below the new crossover frequency. This is also something to consider. We could try to slow the peak time down even more, but then we're going to slow down this tail even more also. And so, there isn't an explicit requirement on settle time, but it's something to keep in mind. So, if we did want to slow it down further, we could iterate on the design, making the crossover frequency even smaller. So that brings us to the conclusion of this lecture. Just to sort of give a little summary. Here we tried to design a LagLead compensator. It had a lag compensator combined with a lead compensator. The reason that we did this is because it gives us extra freedom in our design so that we can try to achieve a certain level of speed of response as well as a certain amount of overshoot, which can be difficult to achieve if we use only a lead by itself or only a lag by itself. The procedure that we followed is the following. First, we design a lead compensator to see if that can achieve all three requirements. It also gives us a benchmark from which to base our design. If we're close, we try to meet the requirements with the lead compensator all by itself, all three of the requirements. If we can't, then we do our lag lead. We start over, we design the lag to achieve the steady state error and the speed of response as indicated by the crossover frequency. We then add a lead compensator to achieve the desired level of overshoot, And of course, we iterate on our design in order to meet all three requirements as close as we desire.